From a quiet corner of Southern California, in the town of San Pedro, emerged one of the most influential minds in contemporary quantum science, John M. Martinis. He was the son of a firefighter who hadn't finished secondary school and a stay-at-home mother devoted to raising her children. Martinis grew up surrounded by tools, wood, gears, and an instinctive attitude towards building things. His father didn't need formal education to show his intelligence. He created with his hands, with intuition, and with patience. That was Martinis' first laboratory. Watching things being put together over and over again lit a unique way of seeing the world. Not through abstract theory, but through what could be touched, built, or broken apart. That direct link between making and understanding would become the very foundation of his future work in quantum physics. During secondary school, he discovered physics, and something clicked. It wasn't just that the equations worked, it was the sudden sense that the universe had structure, coherence, and mystery, like a language waiting to be decoded. Physics offered him a bridge between pure mathematics and the tangible world. Where others saw soulless formulas, Martinis sensed a deep, almost spiritual order, a quiet logic connecting thought with matter. While classmates memorized equations, he dismantled them, tested them against physical reality. He wasn't seeking the right answer, he was chasing meaning. He often spent hours analyzing why a simple law, like ohms, held such beauty in its reliability. This attitude didn't just make him a good student, it laid the foundation for a mindset of discovery. For Martinis, every physical law whispered something fundamental about how the universe held itself together. This kind of sensitivity set him apart, even among his peers. While many students focused on grades or passing exams, Martinis was immersed in understanding why something worked, what hidden law governed a phenomenon, or what mystery lurked in the precision of a circuit. His learning was never out of obligation. It was fueled by genuine wonder. Determined, he enrolled at the University of California, Berkeley, where he quickly stood out. And it was during his final year that he first heard the name of the person who would become his mentor, John Clark, a physicist just beginning to explore the curious overlap between quantum mechanics and electrical devices. With his intuition shaped by years of hands-on observation, Martinis recognized this as fertile ground, a new frontier where the invisible laws of the quantum world might start to reveal themselves in visible electrical systems. He approached Clark, joined his team, and that was the beginning of a journey that would one day challenge the very limits of physical reality. In the early years of his scientific career, John M. Martinis found himself captivated by a question that seemed less technical and more like something lifted from a centuries-old philosophical manuscript. Can a macroscopic object behave like a quantum particle? The question wasn't his own. It came from one of the towering figures in modern physics, Anthony Leggett, Nobel laureate for his groundbreaking work on helium-3 and its superfluid behavior at temperatures near absolute zero. Leggett wasn't just familiar with the quantum world. He had an intuition that we had yet to grasp its true boundaries. Traditionally, quantum mechanics had been reserved for explaining the behavior of the very small, electrons, atoms, subatomic particles. In that domain, reality is not fixed, it is probabilistic. An electron doesn't reside in a single place, but rather in a cloud of possibilities. But Leggett issued a bold challenge. What if quantum mechanics wasn't merely a matter of scale? What if, under the right conditions, those same laws applied to larger systems? to the tangible, visible world around us. This was more than just theoretical speculation. It was a direct rupture with classical thinking, the kind of idea that unsettles centuries of established understanding. It echoed the famous thought experiment of Schrödinger's cat, alive and dead at the same time until observed. But Leggett wasn't interested in metaphor or mental gymnastics. His question was literal. Could a real physical system exhibit that same superposition? This wasn't simply a curiosity for physicists. If proven true, it would mean that the divide between the quantum and classical worlds is not absolute, but conditional. Under the right setup, our everyday reality could reveal traces of the bizarre quantum realm, not in theory, but in measurable outcomes. Not just talk about it, but observe it, measure it, prove it in a laboratory. To answer that, one needed more than a clever idea. It required an experiment capable of isolating quantum behavior long enough to observe it without letting the surrounding environment destroy it. That's the heart of the challenge with the macroscopic world. It's in constant contact with its environment. Heat, light, vibration. Any interaction begins to dequantize it. It loses its coherence. The quantum state collapses. The goal then was to design a system that remained coherent, protected, alive, and observable. This wasn't just an intellectual curiosity. It pointed to something deeper. Could the macroscopic world exist in quantum superposition too? For Martinis, then a young, curious researcher, this was a spark, not something to debate in theory, but something to build. He wasn't driven by speculation. He was driven by the possibility of testing it in the real world. While others saw paradox, he saw potential. His experimental instinct pushed him beyond what-ifs towards circuits, components, cooling systems, and calculations. He turned his attention to a very specific kind of object, superconducting electrical circuits. These systems, if designed with microscopic precision, might just allow quantum behavior to emerge at a scale humans could observe. And so began one of the most daring quests in 20th century physics, to show that a system made of billions of particles could act as a single unified quantum entity. It was an idea that bordered on the impossible, until John M. Martinis decided to build it. When John M. Martinis set out to test Anthony Leggett's proposal, it wasn't just another physics experiment. It was a bold wager to demonstrate that a macroscopic object made up of billions of particles could exhibit behavior that is typically reserved for the quantum world, not in theory, but in a real laboratory. At the heart of his design was a superconducting electrical circuit, but not a conventional one. It was made of materials that, when cooled close to absolute zero, lose all electrical resistance. Within that circuit, Martinis incorporated a crucial component, a Josephson junction, a thin insulating layer sandwiched between two superconductors. This microstructure would allow scientists to observe a remarkable quantum phenomenon, quantum tunneling. To understand tunneling, picture this. You throw a ball against a wall. In classical physics, the ball always bounces back. But in the quantum world, if that ball were a particle or a wave, there's a small but real chance it could simply pass through the wall and appear on the other side. That's what happened in Martinis' circuit. An electrical current, caught behind an energy barrier, would suddenly tunnel through and reappear in a different, measurable state. This behavior, normally seen only at the scale of subatomic particles, was now emerging in a system made of billions of electrons. This alone posed a fundamental question. Where exactly is the boundary between the quantum and classical worlds? If a system so large could exhibit tunneling, then perhaps that boundary is far more flexible than previously assumed. A matter of environment and control, not scale. Martinis knew that the hardest part wasn't just generating such a state, but preserving it long enough to measure it. In macroscopic systems, even the tiniest interaction with the environment, a vibration, a bit of thermal interference, or even a stray photon, can instantly destroy quantum behavior. So the experiment had to be executed in extremely controlled conditions, near perfect vacuum, temperatures below 1 Kelvin, and an architectural design aimed at minimizing external noise. It wasn't the work of a weekend. It took years of refining, trial and error, patience and persistence. But eventually, the outcome was undeniable. Quantum mechanics had been tamed, at least for a moment, in a way that was visible and measurable. And that moment would change how we understand the boundary between the microscopic and the macroscopic forever. This wasn't just about a lone electron. It was about a coherent collective, behaving like a single quantum entity. It was the macroscopic manifestation of quantum tunneling. But Martinis didn't stop there. Within the same circuit, he observed something else extraordinary. The energy of the system didn't behave like it would in a classical circuit, where energy values shift smoothly and continuously. Instead, it was quantized. It could only assume certain discrete energy levels. Just like electrons in an atom can only occupy specific orbitals, the circuit vibrated at exact, measurable frequencies, detectable through microwave spectroscopy. This pattern revealed that the system didn't evolve continuously, but rather in sudden quantum jumps between energy levels, just like atomic systems do. The digital nature of these quantum states provided clear evidence. The circuit behaved like an artificial atom. Martinis published his findings in 1985. While the initial reception was modest, the implications were enormous. In time, his work would be recognized for what it was: the first creation of a macroscopic artificial atom, a human-designed system that mimicked the fundamental behavior of quantum nature. What seemed like a simple experiment became a gateway into a new era. An era in which electrical circuits no longer just conduct electricity. They carry the mysteries of the universe, where what we can touch starts to behave like what we could never reach. And at the center of it all, a chip. Not just a chip that measures, but a chip that challenges the laws we thought we understood. In 1985, John M. Martinis and his team published the results of their experiment in the prestigious journal Physical Review Letters. It was a moment of quiet triumph, the culmination of years of painstaking work. Soon after, a review appeared in Scientific American, highlighting what seemed like a brilliant scientific curiosity: a macroscopic electrical system obeying the laws of quantum mechanics. In itself, this was significant. Scientific American introduced this highly technical work to a much broader audience, signaling that something profound was stirring in the world of superconductors. Yet, despite the praise, the world did not change immediately. The discovery was noticed, certainly, but few truly grasped its importance. Many struggled to fit it into the technological mindset of the time. A question hung in the air. What is this good for? Martinis knew he had no quick answer. What he and his colleagues had shown was deep, but there was no immediate application. It was a bare truth with no apparent utility. It revealed that the universe is stranger and more beautiful than we had believed, yet without any clear promise of revolution. That Scientific American article, though laudatory, reinforced the paradox. The idea was powerful, but its purpose lay dormant. However, that same year brought an event that would change his outlook forever. At a conference held at UC Santa Barbara, Martinis attended the final talk of the event. The speaker was Richard Feynman, one of the most influential physicists of the 20th century. In that lecture, Feynman put forward a radical idea: use the principles of quantum mechanics to perform calculations that would be impossible for a classical computer. This was the seed of what we now call quantum computing. Martinis didn't grasp every detail in that moment. He was young, still a postgraduate student. But something in that lecture struck him deeply, not just because of Feynman's prestige, but because of the boldness of his vision: to take quantum complexity, that apparent chaos, and turn it into a tool. In that auditorium, surrounded by professors, students, and murmurs of unfinished ideas, Martinis began to see his own experiment in a new light. Martinis began to reflect more deeply on the implications of his work. If quantum mechanics could shape the behavior of macroscopic systems, then it wasn't just a theoretical curiosity. It was a doorway, a threshold between worlds, classical and quantum, waiting to be crossed with the right tools, the right minds, and perhaps the right moment in history. What had once seemed like an isolated proof of concept could, in fact, be a crucial first step in a much larger vision. It could be the beginning of a new way of computing, of thinking, of building the future. What began as a simple test of principle gradually became a life's mission, a life dedicated not merely to observing the invisible, but to shaping it. After his pioneering experiment in 1985, John M. Martinis didn't stop. His journey took him to Europe, where he worked alongside physicists such as Michel Devoret and Daniel Estève in France. There he delved deeper into cutting-edge technologies and solidified his understanding of how circuits could be turned into functional quantum systems. Back in the United States, he joined the National Institute of Standards and Technology, NIST, where he worked closely with David Wineland, who would later win the Nobel Prize for his work with ion traps. Surrounded by brilliant minds, Martinis refined not only his theoretical understanding, but also his calling, the art of building. His work ethic, sharpened by years in both academic and experimental environments, became one of his strongest assets. Martinis wasn't simply interested in advancing science for its own sake. He was driven by a practical vision to create something real and useful. He saw every experiment as a prototype, every failure as part of an engineering process. This mindset set him apart in a field where many still leaned heavily on theoretical models. In the late 1990s, an opportunity came his way. A US government agency was looking to fund research into quantum computing. Martinis made a pivotal decision to bet everything on this. He chose not to follow an abstract exploration, but to pursue a concrete mission: to build a real quantum computer. From that moment on, his focus was relentless. At the University of California, Santa Barbara, he assembled a small but dedicated team. They developed systems with 5 and then 9 qubits, fundamental experiments that demonstrated superconducting circuits could behave as stable units of quantum information. However, academia had its limits: scarce resources, long timelines, and slow-moving structures. That's when Google entered the picture. The company, eager to lead the charge in quantum development, offered Martinis and his team the opportunity to scale up. With more funding, infrastructure, and talent at their disposal, they began constructing what would become a historic milestone: a 53-qubit quantum processor that, in 2019, solved a problem in 200 seconds that would have taken the world's most powerful classical computer 10,000 years. This achievement, dubbed quantum supremacy, was met with both skepticism and enthusiasm. But for Martinis, it wasn't just a goal. It was a signal, a sign that the world had changed, that quantum physics was no longer just theory, it was technology. At that moment, the work that had started in a university lab with just a few lines of code and a handful of qubits transformed into the core of a global industry. And Martinis, the builder, solidified his place as one of its fundamental architects. Quantum computing is no longer a promise. It is an emerging reality, and although it is still in its early stages, its potential is already transforming the way we think about information processing. At the heart of this transformation is John M. Martinis, a physicist who not only built some of the first working quantum systems, but also envisages where they could take us next. Unlike classical bits, which can only be a 0 or a 1, qubits can exist in superposition. That is, they can be both 0 and 1 at the same time. This property, combined with quantum entanglement, allows multiple qubits to act as a single, inseparable system with computational power that can grow exponentially beyond any traditional machine. This extraordinary power doesn't manifest in everyday tasks like opening email or browsing the web. Its real value lies in fields where the complexity of a problem grows faster than any conventional computer can handle. One prime example is molecular simulation, predicting how molecules behave at atomic level precision. A quantum computer could model chemical interactions that are currently unreachable with classical hardware. Such capabilities could revolutionize entire industries, from pharmaceutical research to the design of novel materials, designing a protein with tailored functionality, developing an ultra-efficient catalyst, or discovering a new compound for high-density batteries could take decades on classic systems, but potentially days on a quantum one. There is more: artificial intelligence. While modern AI has achieved remarkable feats, it remains limited by the architecture of classical computers. Martinis believes that certain AI algorithms could benefit from quantum processing, not by replacing existing systems, but by expanding their reach, exploring combinations, patterns, and solutions that remain hidden to classical computation. However, he is also acutely aware of the challenges. Today, researchers can control between 50 and 100 qubits, but a truly useful quantum system will require millions of qubits with error correction. To achieve that, we must overcome formidable obstacles: quantum errors, scalability, and above all, decoherence. The tendency for quantum states to collapse under environmental interference. It's as if the magic disappears the moment we shine a light on it. To address these challenges, Martinis does not work alone. He leads collaborations with companies such as Applied Materials, HP, and Global Foundries. Together, they aim to develop technologies capable of fabricating stable, scalable quantum processors. And he is optimistic. Martinis believes that if these challenges are tackled successfully, we could begin to see concrete results within the next decade. This is not wishful thinking, but a projection grounded in progress. Improved fabrication techniques, better error correction codes, and deeper understanding of quantum system dynamics. With each additional qubit, we do more than advance computing. We open another door into the profound laws that govern the universe. In the end, quantum computing is more than just a technological milestone. It is a new lens through which to view reality itself. a way of engaging with nature's most intricate and mysterious patterns. When the Nobel Prize in Physics was announced, John M. Martinis didn't experience it as a moment of triumph. For him, it felt more like a whisper, a quiet signal that decades of silent work, often misunderstood or ignored, had finally left a mark. He wasn't chasing recognition, he was searching for truth, and sometimes truth answers back in the softest of echoes. For Martinis, science has never been just an intellectual pursuit. It's a way of life, a way to engage with mystery. While others chase quick answers, he's always valued asking the right questions, the ones that force us to look again, to build from scratch, to fail and begin anew. Physics, in its purest form, does not erase the unknown. It honors it. It doesn't aim to grasp the entire universe, but to touch it, to feel its edges, to play gently with its laws as though they were the forgotten grammar of nature. Within that playfulness, Martinis discovered purpose, not as certainty, but as a calling. Throughout his journey, he came to understand that every circuit he crafted, every measurement he recorded, every qubit he designed, wasn't merely a tool. Each one was a question, quietly posed to the universe. Not an attempt to conquer, but to listen. And he never walked that path alone. His story is interwoven with people whose names may never grace headlines. Students, engineers, quiet collaborators who believed in the impossible. For Martinis, the Nobel Prize isn't a crown. It's a bridge, connecting generations of seekers. He accepts what was given and offers back what he has built. There's a quiet spirituality in how he speaks about circuits, as if each qubit were a kind of mantra, a glimpse into the deeper order of the cosmos. For him, building isn't merely engineering, it's a form of active meditation, a way to touch the invisible with your hands, a practice in surrender, disciplined and humble, before the great unknown. In the end, quantum isn't just a physical property, it's a living metaphor, a reminder that reality is not fixed, that the universe, like us, is infinite possibility. And that concludes our video. If you enjoyed the content as much as we did, don't forget to subscribe so you don't miss a single episode. Leave a comment below. We'd love to hear your feedback and suggestions for future videos. And don't forget to turn on notifications to stay up to date with all our updates. Thanks for being part of our community. See you in the next video.